Hello everyone, welcome to another Project Wise H2 Math Crash Course. So today we'll be looking at applicational integration. So previously there was another video on mainly theory, but this side focused more on the second part of integration that's usually taught in JC. So I'll first give some general integration advice, followed by the content that's usually taught in applicational integration, as well as some questions and then a quick summary. So some general integration advice is that you can tell that the numbers inside a non-ordinary expression for the matter is greater than 0, then you don't really need the modular sign. So in the case of ln x squared plus 2, you know that x squared is greater than 0, then the 2 means that the entire expression, you don't need the modulus. And so when you can remove the modulus, that will save a lot of time and effort in terms of accounting for the different GLs. Then when you're integrating and there are no limits, remember to add a plus c. If there are limits such as upper limit 3, lower limit 1, then you don't need to have the plus c. Then sometimes some questions will give you two triples as a product of each other. Then how we are going to separate them is using vector form, which is in your M26. Then try hard to find volume through a cylinder plus integral, or like find the volume of sphere. Then you minus one integral. Otherwise you'll usually be finding two integrals again. So that can be more troublesome. Yeah. So this is mainly the theory that's taught in applicational integration. So first there's this part called the Riemann series, which is basically about giant rectangles building up the area under a curve. Then there's definite area as the area under a curve, whether it's about x-axis or y-axis. Then you can also be able to find the area under a curve parametrically. And then last part is on the volume of revolution. So the first thing that you really teach in application of integration is the Riemann series, or in other words, about all these rectangles. So the thing is that actually we can approximate the area under the curve using rectangles, where the width of the rectangles is 1 over n, and the height will be just fx, where x is your like 4 over n, for example. So your height will just be 4 over n or square. And so the thing is that as the rectangles become smaller, they also become more precise. And so you can say that the limit of the series of a rectangle area. So you take the first rectangle plus the second rectangle, you add up all that together, will approximately be equal to the integral of fx, or in other words, the area under the curve. And so the statement is that as n approaches infinity, the total area of rectangles approaches the actual area under the graph. So some questions may ask you about this, and it's quite a standard question. So getting the hang of how to get this summation is a good thing to know. So how we solve this kind of question is that we're going to find a formula for the rectangles using the length times height and spot the pattern between different rectangles. So the pattern will just be we go from 1 over n squared to 2 over n squared to 3 over n squared, so on and so forth. Where we're going to express the sum of the rectangles as a sigma notation where the upper limit is infinity. And then we're going to solve the summation to get the definite area under the curve. So that's mainly about the rectangle part. I'll have a question later to exemplify it. But the next part is basically about finding the definite area under a curve. So in secondary school, you already learned about the area between the curve and the x-axis. So if it's above the x-axis, it's usually given by the integral of fx. But the thing is that if it's below the x-axis, you get a negative area. So how we get the net area is we have to add a negative sign as well. Then in the case where you are finding the area between the curve and the x-axis, and let's say the area is above and below the x-axis, the area will be given by the positive integral above the x-axis minus the negative integral of the area under the x-axis. And we have to do this separately, because if you combine both ranges together, the negative part from 0 to x2 will offset the positive region. That is why we will split it into two integrals from like x1 to x2 and then plus x2 to x3. Then another part will be finding the area between the curve and the y-axis. So if the area is on the left of the axis, the area bounded by the curve is given by the negative of the integral gy. If the area is on the right of the axis, the area is given by positive integral of gy with respect to dy, where x is the subject of the equation. So when we're integrating fx, we make y the subject, so y equal fx. But when we're integrating gy, we make x the subject, so x equal fy. So some example of how we integrate is that we're going to integrate y squared, or we integrate 3y plus 1, or we integrate 22 y squared root plus 89. So it's basically similar to how we will integrate like y equal x squared, but in this case we just swap it around. So yeah, if the area is on the right of the axis, the area is given by the integral of gy dy, where x is the subject of the equation. Then if the area is on the left of the x-axis, And left of the y-axis, the area bounded by the curve is the negative of the integral. Then, likewise, if the area is both on the left and the right, we're going to split it into two regions. So we're going to find the positive integral, which is the right-hand side, and then we're going to minus the negative integral, which is the one below. So you just have to split it into two so that they don't offset each other also. Then about symmetry. So if a function is symmetrical about the x-axis, the area will simply be twice of the area above the x-axis, or if the function is symmetrical about the y-axis, the area is simply twice the area on the right also. So another common question is finding the area between two curves. So for the area between two curves, we're going to take the upper curve area minus the lower curve area. And so make sure you separate the two expressions from each other, then minus the smaller region. So if we are going to find it in terms of dx, we are going to just integrate fx, then we minus the integral of gx to find the area in between. Then similarly, if you want to find the area and integrate with respect to y, we're going to make x the subject, and then you'll just integrate the integral of fy dy minus the integral of gy dy. So in the case of finding the blue area in this instance, it's quite simple, as we just have to integrate y1 over x01 and x02 to get the blue area. So we just integrate fx dx. But if we want to find the green area, we're going to have to take the integral of y1 minus the integral of y2. In other words, take the area of the long curve minus the area of the small curve to get the green area. So we will integrate fx dx minus the integral of gx dx to find the green area. Then the next part is just finding the area under a curve parametrically. So if you want to solve it parametrically, what we have to do is that we have to find the values of t at the range of x values if you want to find the area. And so we also need to find dx dt. And so your new integral will have lower and upper limits in terms of t. Y will be in terms of parametric also, so it will be in terms of t. And you product it by dx dt. So another thing is that we do not want to find the Cartesian equation of the curve, basically. But instead, we're going to use the method of integration by substitution to solve this parametric equation. So, and then the last part is about volume of revolution. So basically, what volume of revolution is that the line about the rotation taking place is always the axis of symmetry for the solid of revolution. And any cross-section of the solid, which is perpendicular to the x-axis of the rotation, is circular. So basically what this means is that if we want to rotate something about the x-axis, like this volume here, if you rotate it, you will create a certain cone like this. And how we actually find this is actually a fixed formula. So if you want to find the volume of revolution about the x-axis, when the region is bounded by the curve fx and the x-axis and the line is equal ax equal b, and we rotate it, the volume of solid revolution is given by pi times the square of fx integrate with respect to x. Then let's say you want to translate the graph to find the volume. We can just find the volume using a new expression. So like if the curve shifts 1 unit backward, we just replace x with x plus 1 and then integrate as usual. So that's just another small thing there. Then if you want to integrate and find the volume of revolution about the y-axis, it's also similar. We're going to find pi and then times the integral of gy all square. And then we integrate with respect to dy. So take note that if you want to find volume of revolution about x-axis, use dx. If it's about y-axis, use dy. And actually what we see is that this square property can actually be really powerful in allowing you to use other trigonometric identities. So like for example, if you have y equals sine inverse x, then we apply sine on both sides. We get x equals sine y, x squared will equal sine square y. And what we can do is that we use our MS26 to get half times 1 minus cosine 2y. So usually use these squares to your advantage and try to make some manipulations so as to make your integration easier. And then there's also the volume of standard shapes, such as a cone, which is 1/3 pi r squared h, or like cylinder, which is just pi r squared h. And so what we can do is that we actually find these areas first, or these volumes first, and then we try and find the volume of y integral. And we just do some minusing, plusing here and there, which will also simplify your solving method. Here another thing they will ask you is finding thickness, which basically means the volume of the outer shape minus the volume of the inner shape. And so this can be like finding the red volume, in other words this semicircle, minus this blue volume will get you this yellow volume. So that's another way, or like another way they can test you also, by finding thickness. So now I'll go through a few questions, mainly finding the volume of solid about x-axis, y-axis, another one where you can use the volume of a circle, in other words, the volume of a sphere. Then there'll be a question on parametric volume as well as Riemann series rectangles. So the first question, they want you to find the integral of e power minus 2x cosine 2x. Then the second part will be something similar, and then we want to find the volume using it. So for this first part, because there are two several parts, the e power minus 2x and the cosine 2x, what we're going to do is we're going to do integration by parts. So we're going to integrate the e power minus 2x, and then we're going to differentiate the cosine 2x. Try when we do that, we get cosine 2x times the negative half of e power minus 2x, the limits there also, minus the integration of minus half times e power minus 2x times minus 2 sine 2x, because we differentiate the cosine 2x. So if we simplify that, you will get half e power minus pi plus half minus the integral of e power minus 2x times sine 2x. Then what happens is that we're going to look at this sine 2x expression again, and we're going to do integration by parts again. Because first we turn the cosine into sine. Now if we do it again, we're going to turn the sine into a cosine. And what happens is that we're going to get eventual result of e to the power minus 2x times cosine 2x dx, which is actually the same answer as the previous part. So what actually happens is that if we look at the final part here, if we integrate e power minus 2x cosine 2x, it equals that half to the power e minus pi plus half minus the integration of pi over 2, 0, e minus 2x cosine 2x. So if we bring this to the left hand side, and we bring this here, we actually got the answer of our integration already. We just need to divide by 2, and we eventually get the answer they want us to show. So actually for this kind of question with sine and cosine, what we can do is that we can try and see this system where we do 2 integration by parts, and then basically we'll show that we can make it the subject and then solve it just like that. You know what? Technically solving the cosine 2x. Yeah. Then for part 2, the region is bounded by the curve y equal e power minus x cosine x, y equal 1, and x equal pi over 2. So if we rotate it 2 pi radius, or in other words 360 degrees about the x-axis, use the result in part 1 to find the exact volume. So for this question, what we're going to do is that we're going to take the volume of a cylinder minus the affected integrated area between the curve and the x-axis. Because when we are doing integration, it's going to find the area between the axis and the curve. So actually, although this is the area we want to find, this is what the calculation will give us. So that's why we're going to take the volume of a cylinder, and then we're going to minus the integrated area. So that's how we get the pi y squared pi over 2 minus pi times y squared dx. So if we put the y squared inside, our y is e power minus x cosine x. Square that, you get this. Then, actually, if we manipulate and get rid of the cosine squared x, we get the cosine 2x, which is actually what we saw in our previous question. That's how we get the cosine 2x. So that's how we try and relate things together so that we can rely on our part 1 answer. So after that, we just find that the final integral expression is pi squared over 2 minus pi over 2, the integral of e power minus 2x, plus the answer we found previously. So once we do that, we can just integrate the e power minus 2x, and we integrate this as well. So when we do that, it will then simplify to pi over 4 times e power minus pi minus 1 minus the integral of this, which will become 4 over 4, 1 plus e power minus pi. Do all this, you simplify all of it. Eventually, you'll get back to this simplified answer, which will be our exact volume of the solid form. And so some learning points for finding the volume of a solid about x-axis is that sines and cosines are usually related together, and we can create a system where if we do integration by parts twice, it can create a certain loop, and we can make this subject, and then as the subject we can just divide by 2, get the final answer of the integration. Or if you want to find the volume, we can do so finding the area of the cylinder first minus the volume we calculate. Because what happens is that the volume we calculate is the volume between the axis and the curves. So that is why we take the volume of the cylinder first minus then the affected area. So that's for question 1. Then the second question is also quite similar, but we just want to find the volume of the solid about the y-axis. So in this question, the shaded region R is bounded by the curve x equal minus 3e to the power minus 2y, x equal half minus e power minus 2y, and the x-axis as shown. So the first part is finding the exact area of the region And then the second part is find the volume of the solid revolution form when r is rotated through 4 right angles, or in other words 360 degrees about the y-axis, giving your answer correct to 2 decimal places. And what this correct to 2 decimal places mean is that we can actually just use our GC to solve the answer, because they do not want an exact answer. So the first part, finding the exact region of R. What we're going to do is that we're going to have our half minus e to power 2y equal our minus 3 e power minus 2y. Because what happens is that we are trying to find the intersection point between the curve. So we have this x line, x equal half minus e power minus 2y, it has this curve. So if we equate them together, we can then find the intersection point. And what this intersection point is that y equal ln 2 over 2, which is this part here, the intersection point. Then why we are going to integrate using y is because we can find this area here. Whereas if we do it split down the middle and find the x coordinate, we will then have to find this area first and this area second. Of course you can do that, but if we can do everything integrate with respect to y, that'll make things a lot easier. So how we found the exact region is that we take the integral of this minus 3 e minus 2y minus the area of this integral, which is just half minus e power minus 2y. And because all this is on the left hand side, this entire thing, we're going to add a minus sign to it. So we integrate this. We will get e power minus 2y divide by the minus 2 here, minus half y minus e power 2y over another minus. So that's how it become a plus. Then our upper and lower limit will be starting from 1, 2 over 2 and then 0. So that's how we get the limit. Because we are finding from this all the way to this. So this is 0, this is 1, 2 over 2 if we draw imaginary line here. Then afterwards you insert the upper limit and so the lower limit. Eventually simplify to ln 2 plus 1 over 4. Then for the second part, it's also going to be similar. We're going to do dy because they say rotating about the y-axis. So that's how we're going to do it. So we're going to take pi y square. The first y square will be this minus 3 power e minus 2y, because if you turn this thing 90 degrees, you'll see that this value is actually greater in terms of the magnitude than x here. Because this has a more negative x value than this. So that's why we will take this first, minus this. And you'll find out that even if you just try and error, that finding this area, finding this volume is greater than finding this volume, which is why when we get the final answer, it's a positive number. If you want to do it the other way around, you take this square minus this square, you get a negative number. And so that's how you can check whether your answer is correct or not. And that's how we get the 4.24. Then for scenario 3, what we actually find is that we have a circle here. So the question is that the curve C1 and C2 have the equation x squared plus y squared equal 4, and then y squared equal 4 over 1 plus x squared respectively. So we want to find the exact coordinates of the point of intersection of C1 and C2. Then we're going to find the area of the shaded region, try the answer to 3 decimal places. Then we're going to find the exact volume of the solid obtained when the shaded region is rotated pi radians around the x-axis. So the plan for this question is that we're just gonna let C1 equal C2 and then find the coordinates. Then we're gonna take the integral of the C1 area minus the integral of the C2 area. Then we're gonna rotate our x-axis. In other words, we're gonna use dx. So we're gonna do pi y squared dx. So we take C1 minus C2 as well. So part 1, we are just gonna let x squared plus 4 over 1 plus x squared equal 4. So basically we get rid of the y squared. This y squared, we replace it with this equation to get this. Then we are going to solve, make x and factorize it, get x squared times x squared minus 3. So we do that. X can either be 0 or x can equal plus minus square root 3. So just account for both the negative and positive value. And then once you do that, we can find our y, and then we can list out all the coordinates here. So usually just list out all the coordinates just to show that there are different coordinates available. Don't just leave it as this, then you don't know which one makes the match. Then for part 2, we want to find the area of the shaded region. So the thing is that due to symmetry, we actually have multiple strategies available. But the main idea is that we want to split the volume into 2 parts using either graph. So for method 1, they want to integrate with respect to y. So what happens is that this area of the shaded region, we are going to take the curve 4 minus y squared allows this circle. We're going to find this smaller area first. Then we add this area. So that's the second part, the 4 over y squared minus 1 square root. So if we do that, we can get you 11.26. And because of the symmetry, this area in the first quadrant is equal to the second area, third area, and fourth area, which is how they multiply by 4. Another way is that you can use dx. So you can find this first. You'll calculate the area from x equals 0 all the way to this intersection point. And then this small part will be between square root 3 and 2. Either way, you'll still get the 11.26. And the thing is that you just need to use symmetry because you can just multiply by 4. So yeah, that's how you can solve this part also quite fast also. Then the last part is finding the exact volume of the solid obtained when the shaded region is located pi radius or the x-axis. So there are 2 methods. We can use the same method as part 2 by using 2 integrations. Or you can take the generic volume of the entire sphere minus the small white area on the diagram. For this question, you just want to find the volume obtained when the shaded region is rotated pi radius or the x-axis. So in this case, there are 2 methods. The first one is finding the integration of this area first. Then second part is finding this smaller integration part here. So what we can do is that when we rotate about the x-axis, what I'm saying is that you'll create something like this. So actually we solve when we do it one time, you'll get all this part where x is greater than 0. So that's why you just need to multiply by 2 so that we can account for the symmetry on this side where x is less than 0. So the first part, we're going to integrate from 0 to square root 3, in other words, all the way to this intersection point, dot down. That's what we find during our first part, or 4 over 1 plus x squared. So yeah, because the integration is pi y squared dx, that's why the y squared become 4 over 1 plus x squared. Then the limit is 0 to square root 3. Then this last part, from square root 3 to 2, it will be the finding the volume of that part of the circle. So 4 minus x squared. So you do that, you insert it in. If you look at your MX26, you'll see that 1 over 1 plus x squared is actually inverse x. So you multiply the 4, that's how you integrate this. Then for this part, you just do the standard integration. So 4 become 4x, and then x squared become x cubed over 3. This over 3 is cubed. Then you have the limits up here, down here is the lower limit. You insert it in, you'll get this final answer. 2 pi over 3 times 4 pi plus 16 minus 9 square root 3 units. Or for method 2, we're going to find the volume of the entire circle minus pi, or basically the white parts here. So 4 minus x squared minus the 4 over 1 plus x squared. So both methods work, it's just which one you prefer. So some key learning points is that we have to account for both the positive and negative values of x and y respectively. To find the area, it can be split into 2 areas depending on the x and y intersections. And so we can use, there are 2 ways you can do it. There are multiple methods, and in some cases, you can actually use dy or you can use dx. It's ultimately which one you find more simple to integrate. Then we can also use the volume of spheres, prisms, rectangles where possible. And sometimes it can save more time and effort. For scenario 4, this will be based on parametric equations. So they give you x equal 3 sine t and y equal 1 plus cosine t, where you have the limits of 0 less than or equal to t, which is less than or equal to pi over 2. So the first part is just sketching the graph. You can do that using a GC. Then secondly, find in terms of A, the area bound by C, both axes and the line s equal 3 sine A, where A is a constant less than pi over 2. Then by finding the Cartesian equation of C, find the volume of revolution when the region bounded by C, the line y equal 1 over 3x, and the y-axis are rotated about the y-axis. So the first part is just a sketch. It shouldn't be too serious. Just make sure that for your window, you know where the x equals 0 and the x equals 3 is. But right, as long as you change your settings such that your range for t is 0 and pi over 2, you should be able to get this. Then just remember that we're going to have black dots here because they imply that we include those specific values of t equals 0 and t equals pi over 2 And another thing, you just have the coordinates of the endpoints in x and y respectively. Then for part 2, you want to find the area. So the area required is just going to be the integration of y dx. We're going to have the upper limit as 3 sine a and lower limit as 0. So we're going to do that. We insert both of them in. So we have y, but then because it's still in dx, we need to turn it into dt. So what we do is that we're going to have a dx dt here, which is how we get our 3 cosine t. So we do that and then expand everything. We get the integration of 3 times cosine t plus cosine square t. This cosine square t, we need to get rid of it. So how we get rid of it is using our M26. So we get cosine 2t plus 1 over 2. So after that, we can just do integration. We get 3 times sine t plus half of this expression. So sine 2t over 2 plus t. Insert the upper limits, insert the lower limit. It will simplify till we get 3 over 4 times 4 sine a plus sine 2a plus 2a. And last part is just finding the volume, where we have this restricted area. So we set up this curve, and then we are going to have the area bounded by the line y equal 1 over 3x and the y-axis. And we're going to rotate it about the y-axis. So how we do this is that actually we can split it into 2 parts. So when we integrate it, we're going to have this somewhat hemisphere, and then have this bottom part, which is basically a cone. So actually, to find this area, we can find it in terms of this. Our first part is just finding the Cartesian equation. And so how we find the Cartesian equation is that usually we want to make use of the sine square plus cosine square. First, we already have a sine here, or cosine here. So what we're going to do is that we're going to make of sine t the subject, of cosine t the subject, and we're going to force fit a sine square t and a cosine square t here, which is how we get this. Then, from here, we're going to find the, because they want to ask about rotating about y-axis, so we're going to use dy. So we're going to integrate x squared dy here. So that's the first part, which we will find this region, this upper region. Then this down part is just going to be finding the area of the cone, or the volume of the cone. It's going to be 1/3 pi r squared, so the r is 3, times the height, which is just 1. So in this case, it will be 9 pi times 1 minus 1 y minus 1 squared dy plus 3 pi. Insert it into your GC, you'll get 28.3, or in other words, 9 pi. Then for the last question, is basically about the Riemann series rectangles. So there's a few parts to this, but first part is quite simple. They just want to find the integration of this. So for this first part, we're just going to look at our MS26 for reference. So we have an x square here, and we have a 4, which is basically a 2 square. So if we do this, we look at MS26, we'll end up getting a sine inverse x over 2, 1 here, 0 here, put the upper and lower limits here, you simplify, you'll get pi over 6. So that's the more straightforward part. The part that is unique to this question is that they will show the graph of y equal 1 over square root of 4 minus x squared, and say with the aid of a diagram, explain why the value of 1 over n times this expression gives an approximate answer to part 1. So the thing is that whenever you get these questions, what we're going to do is that we're going to draw a bunch of rectangles. So this is what the rectangles are. So if you want to get the 1 over n here, we need this 1 over n here also. So we're going to have these rectangles of width 1 over n, then the height is going to be f1 over n. So that's how you get that. And the second one is also going to be a width of 1 over n. Cos 2 over n minus 1 over n is just 1 over n. So the width always is 1 over n throughout, and the height is also going to be f 1 over n. So what happens is that if you want to find the total area of these rectangles, the summation of the rectangle is basically the interval of 1 over n times fx. So 1 over n times, sorry for the blurry image, but basically the same thing, f1 over n, 2 over n, so on and so forth. And so what happens is that we can simplify this into basically 1 over n plus our fx. So the fx is just going to be 1 over 4 minus our 1 over n squared. We add all this up, it's basically the same thing as what our answer is. So basically, we are trying to imply that A is the sum of the areas of n rectangles with width 1 over n from x equals 0 to x equals 1. And since the integral is the area on the curve, the A is the approximate answer to the answer in part 1. Then for the last few parts, they say state a reason whether A is a larger value than the actual answer. And so you realize that when you make this rectangle, there's this small area which is above the curve. And because of that, that means that the A overestimates the area under the curve. And so A has a larger value. Then lastly for part 4, you just want to state the limit. And as we know the limit, it's basically the area under the curve, which in other words is just the answer in part 1. So that's why our final answer will just be part over 6. Yeah. So some key learning points for any question with these rectangles is that the area under the curve is a summation of rectangles, and these rectangles have a breadth of 1 over n and a height of fx. And the limit of this total area of rectangles is equal to the area under the curve, which is the integral of fx. And so the sum of rectangles is either an overestimate or underestimate depending on the rectangle's use. Let's imagine if we start with f0. If we start with f0, the rectangle will be like smaller from the start of this f0 all the way here, go down. So it doesn't include this upper part, but rather it doesn't even have a smaller part here. How to show, but basically it starts from here, go down. So that's how it will become an underestimate. But in this case, we are looking at this endpoint at 1 over n, which is why I have an overestimate. So yeah, that's how it can either be an overestimate or underestimate, depending on what kind of rectangles we use. Yeah, so this is basically a list of some of the stuff that you can memorize for integration in advance. The first 3 parts is mainly from our theory part. This is about integration by parts and what we should choose to differentiate first. So all those things that you see in MF26 or logarithms, we try and differentiate them first. Then for the area between curve and x-axis, y-axis, area between 2 curves, for the revolution, this is basically the stuff and the formulas that you need to use. Then you want to integrate the product of 2 triangles, we use factor formula first to break it down. Or if you want to translate a graph, we just change the x or the y value. So that's all I have for this part. Hope you learned something from this video and hope to see you in the next crash course. Bye!